Hello folks, today we're going to be looking at goodness of fit tests, and as it says here we're going to be using the chi-squared distribution, so this is the Greek letter chi, to test whether observed discrete data follows a particular model. So this type of test can be used for any discrete data, which makes it very, very useful. Okay, so we're going to go straight in by thinking about an example. So here we've got a die that's been rolled 120 times, and these are the observed frequencies of each of the possible outcomes. And we can look at those, and it might well bring up the question about whether the die is fair or not. Obviously, if it was a fair die, we would expect these frequencies to be quite similar, and they do look reasonably similar, some a bit high and some a bit low, but they are reasonably similar. And in fact we can go further than that, because if we know that it's rolled 120 times, we could say that we would expect there to be 20 of each. Obviously we wouldn't expect exactly those results, but something similar. So to test whether the die is fair, really we're looking to see what the differences are between these observed values and the expected values. And that's what the goodness of fit test does. And to do it, it uses a test statistic, the x-squared test statistic, which is the sum of the differences between the observed and the frequencies, all squared, divided by the expected frequency for each pair. Okay, so why is it squared? Well, first of all, if we take these differences, so observed minus expected, we can see this one would come out to be positive 3, this one would be negative 5. When we summed those, obviously the positives and negatives would cancel each other out, so we don't want that. So we square them all to get rid of the negatives, basically. And we want this measure to be a kind of proportional measure to the expected value, so that's why we divide by the expected value there. It should be noted that there's another form of this formula, and it can be shown that these two are equivalent. N is the number of observed values, the total number of observed values. It's called the x-squared value simply because we're squaring these. It's nothing to do with actually squaring an amount. Okay. And it can be shown that that test statistic follows at the chi-squared family of distributions, and that is providing that all expected values are greater than or equal to 5. So we've got to ensure that all expected values are greater than or equal to 5 to be able to use the chi-squared distribution to test statistic. So if any of them are less than 5, then what we need to do is combine the frequencies, so put some of them together until they are at least 5. So if we go back to this example, our expected frequencies here are all 20, so it's not a problem. However, if any of them, say this one had come out to be 4, then what we'd have to do is combine these two outcomes, the 5 and the 6, so that we'd get an expected value of greater than or equal to 5. But we'll have a look at an example of that later. So the chi-squared distribution has one parameter, and it's this Greek letter nu, the degrees of freedom, and that can be thought of as the number of cells minus the number of constraints, or perhaps more easily thought of as the number of values that can vary. So if we know the total number of observations, how many of the observed outcomes can vary, and that will become clearer, I think, with the example again. So we'll go back to that example we were just looking at, and we might want to test whether this is a fair die. And another way of thinking about that is whether or not the observed frequencies, these frequencies, could be modelled by a discrete uniform distribution. So if it was a fair die, we would expect it to follow a discrete uniform distribution, which would have these expected outcomes. So, as with all hypothesis tests, we start with our null hypothesis. The null hypothesis would assume that it does follow that distribution, and because we're testing that, the alternative is that it cannot be modelled by that distribution. Okay. So, new, the degrees of freedom. Well, the degrees of freedom is the number of observed values that can vary. So we know that there were 120 rolls altogether. Hopefully you're happy that if once these 5 observed frequencies are known, this one would be set in stone, alright, because they've got to add up to 120 altogether. Hence there are only 5 that can vary. So it's basically the number of columns, which is 6, minus 1 that can't vary. So the degrees of freedom would be 5. We then need a critical value to compare our test statistic to, and the critical value can be got from the chi-squared tables. So we can go to our formula book or at the back of your textbook, and we get this table here. Okay, the degrees of freedom is down the left, and along the top here is the probability that exceeds the amount. So it's a bit different to the other cumulative tables that you've had for the Poisson binomial, because this is the area to the right. Okay, so if we look back at our example, and we want to test at the 5% significance level, that means we want 5% to the right, and we want chi-squared, degrees of freedom equal to 5. So in the table, degrees of freedom equal to 5, which is there. We want 5% to the left, so 0.05, to the right, which is there. So our chi-squared value is equal to 11.070. Okay, so you get your critical value from that. Okay, with all goodness of fit tests, the alternative hypothesis will come along if there's a big difference between the O's and the E's. So that would make this value large. And hence the critical region is always going to be at the top end of the chi-squared distribution. So this is the shape of the chi-squared distribution, and our critical region will always be at the top end. So anything greater than 11.070. So then we have to work out our test statistic. So we're going to subtract the O's and the E's and then square them. So it doesn't matter which way you subtract them, because you're going to square them, it'll make it positive anyway, and then divide by E for each one. So for the first one, 3 minus 20 is 3, square it is 9, and divide by 20 will give you 0.45. And you can do that for the same, or in the same way for all the others. And then our formula told us to find the sum of those values. So here I've got an extra column that's got the total of all of these values, which is 3.4. And we can picture 3.4 on our sketch of the chi-squared distribution. We can see it's well below 11.070. It's not in the critical region. And if it's not in the critical region, we always accept the null hypothesis. So we can say 3.4 is less than our critical value, 11.070, so we do not reject H0. And as usual, we have to put that in the context of the question, so there is no evidence that the die is biased. And that's basically it for a goodness of fit test, but we'll look at a few more examples where it varies a little bit. So first there's one here for you to try, very similar to the last question. So give it a go, pause the video, and then you can look through the solution. Okay, so for this one here, null hypothesis and alternative hypothesis are the same as in the last question. The degrees of freedom will be 2 because there's 3 observed values, but one of them will be set in stone if we know the total. So degrees of freedom is 2. Critical value from the table comes out to be 9.210. This is with 1% significance level, so 1% to the right, 0.01. And we can work out our O minus E all squared over E values and find the total of those, which comes out to be 7. And then we compare that to our critical value. Again, it's less than our critical value, so it doesn't land in the critical region or fall in the critical region, so we do not reject H0, and we cannot conclude that the spinner is biased. We would accept that it is an unbiased spinner. Okay, so there's a general method here for the goodness of fit test that will work for any discrete distribution. So far we've just looked at discrete uniform distribution, but we could try it with other discrete distributions, so that's what we're going to do next, look at a binomial example and a Poisson example. But you might just want to have a quick look through all of these steps, pause the video before the next example. Okay, so testing a binomial distribution. Here we've got data that is thought to be modelled by a binomial distribution with n equal to 10 and p equal to 0.2. And it suggests using the table for the binomial cumulative distribution function to find the expected values. So we'll have a look at how we do that and conduct a test to see if this is a good model, 5% significance level. So here are our frequencies. The null hypothesis is that that distribution is a suitable model, and the alternative therefore is that it's not. N in this case, well, we can add up our observed frequencies and n comes out to be 100. What we would need to do is think about how many of each value we would expect to get if this was indeed the correct model, right, or a suitable model. So we can find out the probability that x equals 0, and we can do that straight from the tables. So if we go to the tables here, what have we got? So this is the chi-squared. We need to find the binomial, and we had n equal to 10. So here we've got n equal to 10, and we wanted the probability to be 0.2, so it's the fourth column. Alright, so the probability of 0 or less, which is just 0, is 0.1074. And so sorry, so this one here comes out to be that 0.1074. Now we know that there's 100 altogether, n is 100, so how many would we expect to get? Well, that's just the probability times 100. So for some reason it says 10.75 here, it should say 10.74, sorry. And then to get the probability that x equals 1, well, we could use the formula, and it's absolutely fine to use the formula, but because we've got to work out a few here, I think it's generally easier to use the table when possible. So if we go back to the table again, if we want the probability that x equals 1, well, this is the probability that x is less than or equal to 1. If we subtract the probability that x is less than or equal to 0, we're just left with the probability that x equals 1. So you do a subtraction there, and if we do that, you will find it comes out to be 0.2684. And again, times that by 100 to get the expected value. And you can just keep doing that to get all of these probabilities and then expected values. And once you've done that, you might spot, if you've remembered, you might spot a problem because we've got several expected values here that are less than 5, and we need them to be greater than or equal to 5 to be able to use the chi-squared distribution. And in fact, even if we add these 4 up, I believe it's still going to be less than 5. So what we're going to have to do is put these 5 columns together. Alright, so we're now going to have a new table with x values of 0, 1, 2, 3 and then 4 and above. Okay, so to do that, our expected values are going to be the 10.75 there, what's corrected here, 10.74, 26.84, 30.2, 20.13, and then to get the last one we're going to add all of these together. So our last column will have an expected value of 12.09. The observeds are just straight from here, so 12, 28, 28, 17, and then we're combining these 5, so it comes out to be 15. And we can work out our O minus E all squared over E for each one, and by adding those up we will get our test statistic. And our test statistic then comes out to be 1.5453. Okay. Degrees of freedom, you have to remember to use the table that you ended up with. So we're not going to use the original one. This is the table we're testing. So it's got 5 columns, but one of those observed values would be set in stone when we know the others. So degrees of freedom will equal 4. We can then go to our chi-squared table to get our critical value, which comes out to be 9.488, and so we can clearly see here that our test statistic is lower than that. It hasn't fallen in the critical region, so we do not reject H0. So we can say in the context of the question that this binomial distribution is a possible model for the data. Okay, so quite a lot of work there, but really you've just got to follow the steps, and you should get there. There's another example here which is very similar. Again, it's a binomial distribution that we're testing, but we're not given the value of p, so we're not given an exact binomial distribution to test. So in this situation we have to actually estimate the value of p. We're given n, we're told there's 100 families, which is just the sum of these. Okay, so I'm not going to go all the way through this, but the differences I'll point out. So to estimate our value of p, well, it's all about the proportion of girls basically. So the best estimate of p would be thinking about how many girls there are in total out of how many children. And to get the number of girls, we can multiply the number of girls by the frequencies, by the number of families, and that comes out to be 199, and we divide that by the number of families altogether, which is the sum of these frequencies here, or we can just say, well, it's 5 children, 100 goes, so that's 500 at the bottom. So our best estimate of p comes out to be 0.398. Okay, and it should be noted that another difference is that when you estimate a parameter, that is an extra constraint. Okay, so well, actually I'll come to that in a minute. So we can get our probabilities here based on a binomial distribution with n 100 and p equal to 0.398. I can find the expected values based on those. N is 100 again, so I'm just timesing by 100. Again, I've got a problem here because that's less than 5, so I'm going to have to combine some of these. So I'm going to combine these two final columns, which gives us this table here. Alright, and in this example they've actually used the other formula, which is just the O squared over E. Alright, so I've just worked out that for each one, which is slightly quicker than the other method. It comes out to be 107.22. And it's the degrees of freedom that we have to be a bit careful with here, because with this table there are 5 columns. One of those would be set in stone, so that takes us to 4 degrees of freedom, but then because we've estimated p, then that's an extra constraint. So actually we subtract 2 from our 5 columns, it gives us degrees of freedom 3. Alright, critical value, we can get from the table. The test statistic using this formula is the sum of these, so the 107.22 minus n, which is 100, so that comes out to be 7.22. And again, that is just below the critical value, so we do not reject H0. The binomial, we can say, is a suitable model. One final example using the Poisson distribution. So here we've got the numbers of telephone calls arriving at an exchange in 6-minute periods were recorded over a period of 8 hours with the following results. Can these results be modelled by a Poisson distribution? So again here we're told we're testing a Poisson distribution, but we haven't been given a value of lambda, so we're going to have to estimate that. So null hypothesis, Poisson is a suitable model. Alternative, it is not. The number of observations actually can be worked out because we know that we've got 8 hours, so that's 8 times 60 minutes, but then in 6-minute periods, so divide by 6. So there are 80 periods here. We can estimate our value of lambda by finding out how many calls there were altogether. So that's multiplying these values and then dividing it by the number of time periods, 80, so that comes out to be 2.2. Alright, so it's averaging 2.2 calls in each 6-minute period. And again, because we've estimated that, that's going to be an extra constraint when it comes to finding the degrees of freedom. We can use the Poisson tables to get a probability of 0 when lambda is 2.2, so that comes out to be 0.1108, and we multiply that by 80 this time to find out the expected number of times, the expected number of 6-minute periods we'd expect that to happen in. And we can do that in each of the other ones. And because this table we're assuming gives us all the data, so we're assuming that 9 would be 0, 10 would be 0, 11 would be 0, and so on. So our last column, in fact, is just 7 or more. Okay, and to work out the expected value there, well, what we can do is just add all of these up and subtract it. Okay, so that would be subtracting it from 80. Okay, so this is just 1 minus all of those, and then we've multiplied that by 80 to get there. Alright, should be the same as if you add all of these and subtract from 80. Okay, again here we've got an expected value less than 5, and here, but putting those 3 together will make the expected value 5 or more, so I've just combined those final 3 rows, so now we've got a greater than or equal to 5, so that's these ones combined. Expected value for that would be these 3 expected values adding up to get 7, and we can add up the expected frequencies to get 3.808. Work out the O minus E all squared over E for each one and add them together, and our test statistic comes out to be, looks like 2.1016 for that. Degrees of freedom, well, here there are 6 rows, we subtract 1, we subtract another because we've estimated lambda, so our degrees of freedom is going to be 4, and we were told a 5% significance level, so the chi-squared value there comes out to be 9.488. Our test statistic is this time, sorry, that should be a less than, shouldn't it? So again, it's not in the critical region, so there is no evidence to reject the null hypothesis. So calls may be modelled by a Poisson distribution with lambda equal to 2.2. Okay, so that's goodness of fit tests. Sorry, quite a long video, but quite a lot to get through. Obviously, if you've got any issues, you can ask me in the next lesson, and hopefully you'll be good to go on some questions. Okay, thanks, bye bye.